In this video, we are going to imagine that we are riding a Ferris wheel. And we want to find out what our height above the ground is going to be as we are riding around this Ferris wheel. So imagine we are riding around a particular Ferris wheel, and in our case, in activity 2 here, we are going to imagine that we are riding the Brown County Ferris wheel that has a diameter of 30 meters and it completes one full revolution every 2 minutes. How high above the ground are we as we are first entering the Ferris wheel, going around it once, going around it twice? We have a little bit additional information about this Ferris wheel. It also tells us that we are still 5 meters above the ground as we are entering the Ferris wheel. And we know the diameter is 30 meters, and we know that one full revolution takes 2 minutes. So one full revolution takes 2 minutes. So imagine we are entering our Ferris wheel over here. So we have a schematic, and we can include a little bit of the data from the problem on our sketch right here. So this is when we are entering the Ferris wheel. And down here, let's say this is the ground. So this is the ground. So this is height 0. And then here we have different heights going up. And so what did they tell us? They tell us at the lowest point over here, we are still 5 meters above the ground. So I can put that here. This is 5 meters. And the diameter is 30 meters. So the highest point of our Ferris wheel right here, I can label that 2. That is going to be 35 meters. Since we have 5 meters to get to the bottom of the wheel, and then an additional 30 meters to get us all the way through. The center of our Ferris wheel, we can also indicate how high that is. Well, the radius of this wheel is 15 meters, and then we have the additional 5 meters over here, so that is 20. And we could label lots of other points. So every tick mark here apparently they are 5 meters apart. So we're going, our bottommost one is 5 meters, and then we'd get 10 meters, and then we'd have 15. We have 25, and then we have 30 right here, and the highest point would be 35 meters. We are riding around the Ferris wheel. We're going counterclockwise, so we are entering right here, and then we're going counterclockwise. And we are entering this at t equals 0 minutes, or seconds rather. And we're going around counterclockwise. And it's taking us 2 minutes to complete one full revolution. So as we're going around the circle, we are going to reach the bottommost point again also at t equals 120 seconds. I would like to use seconds because it just gives us more intermediate times that we can talk about. It's a little bit easier to do this problem in seconds. Where else? When are we going to be at different points? Well, if it takes us 2 minutes to go all the way around the Ferris wheel, then at t equals 60 minutes, we're going to be at the top. And at t equals seconds, at t equals 60 seconds, we're going to be at the top, and at time t equals 30 seconds, we are 1/4 around, and so on. We could indicate a lot more points over here. We want to graph just the height as a function of time. So I'm going to go down to our graph right here and plot some of these points that we've discussed. So if we're just concentrating on the height above the ground, then at the beginning, when we are at this point right here on the Ferris wheel, when we're entering, we are 5 meters above the ground. So I can indicate that point by saying at t equals 0, we are at 5 meters above the ground. So we are entering our Ferris wheel right here. And since it takes us a full 2 minutes to go all the way around, we will hit this point again after 2 minutes. And then we're going to hit it again after another 2 minutes. So we will get to this point every 2 minutes. When do we reach the highest point? Well, we said that's after 60 seconds. So here we have 60 seconds. And the height after 60 seconds is a full 35 meters. So that gives us this point on the graph at t equals 60 and h equals 35. We will hit that point again also 2 minutes later, so that's after 180 seconds, so we will hit that point again over there. And then we indicated over here that we're going to be at 1/4 up after 30 seconds, so we can indicate that point as well. We get that as t equals 30, that is over here, and the height is 20 meters, so we get to that point over there. And then again 2 minutes later, or 120 seconds later, at 150 seconds we will be at that point again. We will reach that same height. Now you notice we're going to reach that height again on the way down as well. That happens after 90 seconds. So we reach that same height actually also after 90 seconds, so I can indicate that right here, and then also after 210 seconds. So it looks like, I mean, as we're going around the circle, we're going up, we're going down, we're going up, we're going down. Now the question is, how should I connect those points in between, since I will reach every single height in between? To help us figure that out, let's see where we are after 15 seconds. So 15 seconds is down here. And after 15 seconds, we are along the path, along the circle right here. We are halfway along this path. So halfway along this path is over here. That is 1/8 of the circle. And what is our height? So even though we've covered half the distance along this quarter circle, in terms of height, we've only risen a little bit. So we are still less than 10 meters off the ground. So we are about here. And we can see the next 15 seconds, we're covering a lot more ground. That is a lot more ground, even though it takes the same amount of time. During those 15 seconds, we covered a lot more ground. And the same thing is going to happen if we did this for the next 15 seconds. So at 45 seconds, we are about over here. Again, we are at another quarter of the circle, but we've reached just over, oh, actually, let me put that, it's more like here, just over 30 meters. So we are about here. So connecting the dots, it looks like we are getting a shape that looks somewhat like this. And if I draw this carefully, I could plot a few more points, but you can convince yourself by doing that the graph of the height of somebody riding the Ferris wheel is going to look like this wave. We call this a periodic function because it keeps doing the same thing over and over and over again. I could shift my function over and it fits itself exactly. We are repeating the same motion over and over again. We go through the same values over and over again. And looking at this, we can describe this wave-like. So this is like a wave-like shape in terms of a few important features. So one thing that we can talk about is the period. And the period is the horizontal distance that it takes for the graph to complete one full cycle. So this period is, in our case, the time it takes to complete one full cycle. So it took us from t equals 0 to t equals 120 to go once around the Ferris wheel and to complete one complete cycle of our graph. So in our case, the period is 120 seconds. A second feature that we can talk about is the midline. The midline is a horizontal line midway between the function's maximum and minimum output values. So we can see the midline in our graph right here. And in our case, the meaning of this midline is actually the location of the center of our Ferris wheel. That central point is 20 meters above the ground, and as you're riding around the Ferris wheel, you will sometimes be above 20 meters and sometimes below 20 meters. So in our case, the midline is a height, and it's 20 meters. And then a third important point is the amplitude of this function. And the amplitude is the vertical distance between the function's maximum value and the midline. So it tells us how far above the midline do we get at most. And incidentally, that's also the same as the distance we will dip below the midline. But in our case, it represents the radius of our Ferris wheel, and that is 15 meters. You can see the definitions of these terms in the box below the graph. So a function is called periodic if its output values repeat at regular intervals. Graphically, this means that if the graph of f shifts horizontally by p units, the new graph is identical to the original. Given a periodic function f, the period is the horizontal distance that it takes for a graph to complete one full cycle. That is, if p is a period, then f of t plus p is f of t, because every p units we are going through the same cycle. The midline is the horizontal line midway between the function's maximum and minimum output values, and the amplitude is the vertical distance between the function's maximum value and the midline. So we already answered the questions posed below the box up here to the right of our graph.